All right, welcome back. So today is January the 21st, and we're going to continue here in chapter 13, and we're talking about the 4 different regions in the infrared. The first region represents the hydrogen region, which contains the OH groups, your alcohols and your carboxylic acids. Those are really intense bands that range between 3550 to 3200. Notice that these are high numbers. The higher the number, the higher the energy. All right, remember that. Okay, because that might be in a quiz, on the quiz next for you guys in the lab next week. And then the next one will be the NH region, which includes the amine, the primary amines, secondary amines. The primary amines, for each hydrogen in the nitrogen, you will have a peak. So the primary amines will have like 2 little peaks, and they're not really big. And the secondary amines will have 1 H. So for each H, there will be 1 peak, right? And then for the secondary amines, you will have 1 peak. And then for the tertiary amines, you'll have a flat line. So it will not help you out there. So you can identify the R part, but not the nitrogen part here, unfortunately. But if you have a nitrogen on your structure, then you know that you can still assign it. All right. Then the next 3 hydrogens are the most interesting ones. Those are the CH hydrogens. And as we know, we have 3 hybridizations for carbons containing hydrogens. The first one is the triple bonds, which are what we will be calling them SPCH character. Then that's a sharp band. This is a sharp band, really sharp band, right around exactly almost all the time at 3300. When I mean sharp, it's sharp like that. And then we had something very cool, very important. Right at 3000, the sp2CHs share the limits with the sp3CHs. And this line here at 3000, we call it, or I call it, the magic line. All right. And usually when I start an infrared identification, that's the first thing I trace. I trace a line right at 3000, and you'll see how I do it. I'm going to teach you how to do it. All right. And so anything past 3000 is sp2ch in character, and that goes from 3100 to 3000. And anything prior to 3000 is sp3ch in character. So that would be this. So past 3000 is double bonds, could be aromatics or aliphatic double bonds. And before 3000, between 3000 and 2850, you will have the sp3CHs, these are the tetrahedral CHs. All right, and then you'll have the aldehydes. The aldehydes show up around 2830 to 2700. Notice that we have to, since we're used to reading from left to right in the Western Hemisphere, we have to mention the higher number here because we're looking at higher energy on the left, lower energy on the right side. All right, so that's why it's kind of weird. You could say, oh, this is the range, 2830 to 2700, but that's how we have to read it. And this will be 2 bands, and they usually look like this. One is a little long, not really long, it's like a little lower than the other one, but they're about the same in height or intensity. All right, and I call that myself. This is my way of remembering it. I call it the 2 horns. You will see them. They look like 2 horns to me, and I don't know, but that helped me when I was a student. So I'm just gonna keep calling it the 2 horns, and you can call it whatever you want, but I'm just gonna give you that as a study aid. All right. Then the next region is the triple bond, and the triple bond region contains two groups. You have the nitrile groups and the internal triple bonds. Actually, internal or terminal, they will show in there because that's an inflection between the C and the triple bond C. So, so imagine you have three rubber bands there instead of the three bonds, and they're stretching. That's what that signal is. And because you have too many bonds, those two atoms of carbon, they will not move that much. All right, and that's why it's less intense. Both of these signals are weak. All right. Also, you can see symmetrical alkynes. For symmetrical alkynes, it's even weaker because you have almost a net zero dipole. All right. The next region is the double bond. So double bond. We have the most important is the carbonyl, which usually runs around in the 1700s. Then we have the imine group. The imine group is used in OCHEM, but I don't know if we'll see a lot of examples of that here. It's mostly for like advanced OCHEM. And then we have the double bond ones. So here are the different ranges where you can find them. For the double bonds, usually it's 1660 to 1640. And then we have the C double bond, C stretch of aromatic groups. These ones are usually four really intense bands that are pretty much combined with the fingerprint region. All right. A lot of books, like I said, they actually put this on the fingerprint region because it almost looks like it belongs there. But this is still a double bond, so it should be here in the double bond region. All right. And then the nitro group, we're not going to talk about it. I don't think I haven't had any examples of that in class, but I think I have. I don't know if I have one here. I think I might have put one in here. If not, we can live with it. It's very rare anyways. All right. So I think this is the last slide when I stopped last time, and we have a little worksheet here that I usually give to my students. Let's see if I can find it real quick. All right, so that will be on important handouts. So it will be this one. So let me open this and save it as in class. So I'm going to save this as in class. All right, so basically here I'll have this handout for you on the next milestone. So basically all you got to do is to draw the functional group to remind you. While you're doing that, you will remember the baseline position of the carbonyl absorption. So for the ketones, you have this. You don't need to draw the C. You do that. That would be 1715. Aldehydes is an R with a carbonyl and an H. These are 1730. So for the aldehyde here, now you're thinking, okay, besides the carbonyl, I need to have the two horns in the CH region. Remember that? So you need to start thinking about those things. For the carboxylic acid, yes, you will have a carbonyl peak at 1710. It's a little shorter than, it's the one that is the one with the lesser number. And so here you have two things. Besides the OH, besides the carbonyl, I'm sorry, you have a carbon oxygen stretch in the fingerprint region, and you will have an OH huge V-shaped band in the hydrogen region. Then the esters, will look like this. Hold on a second. That was ugly. I know why. I'm drawing with my laptop upright. That's not fun. So here you have a carbonyl that shows up at 1740. You have a CO stretch. Actually, you have two CO stretches, but you might be able to see two CO stretches here. Sometimes they merge. All right. And what I mean by CO stretch, it's this one. You have this one going this way, or you have this one right here. So you have two different CO stretches, and therefore you might have two. Your CO stretch will be maybe two peaks, or a broad one that is combined, that looks like really fat. All right. And then the other one is the anhydrides. The anhydrides will be these guys, where they share an oxygen, and their bands for the carbonyl peak starts at 1820 to 1750. And notice that you will have two bands, and especially if the R groups are different, you might have an R group on the left and one prime on the right side. Those carbonyls will be completely different. So you can expect two strong carbonyl peaks there. And then you have the acyl chlorides. I have an example here that goes at 1800, and the amides. The amides will be interesting because they will have two little blips, two little peaks for the nitrogens, the NHs. So with two, or if you have an R, like if it is like this, and an R prime, then you will have one peak, and none if you have two R primes. All right, so here are the numbers for that: 1690 to 1650. And so this baseline, so you'll have this chart. You just have to fill this part, and that will help you get started. All right. So check this out, what it says in here. This is the thing, though. In chemistry, nothing is so precise and accurate. There's always exceptions, and there's always rules. So here are a couple of rules for the conjugations. The conjugation of carbonyl groups will shift the signal to a lower position by 20 to 40 reciprocal centimeters. All right. Now, if the carbon of the carbonyl is inside of a 5-member ring, it will shift to a higher position by 30. So one thing to remember, okay, you have 20, 30, 40 here involved. So just put 20, 40 in the top and 30 in the bottom. All right. And so check this out. For example, let me flip my computer because I think my handwriting is suffering right now. So I have this. Say, for example, you have this aldehyde versus, I always give this classical example. So check this out. The signal for the carbonyl for this aldehyde on the left is approximately 1730 reciprocal centimeters. Now, what if I don't know the number for that one? Okay, so which number do I start here with? out of this. What is this? What kind of, this is a lactam, but a lactam is what? What functional group of these ones? It's this molecule. Anybody? Take a shot. What does it look like to you?
A carboxylic acid?
Good guess, but it's not.
An ester?
It's an ester, yes. So notice that you have a carbonyl. So this is your R group here. Carbonyl, oxygen, carbonyl. All right. I'm sorry. R, which is carbon, carbonyl, oxygen, carbon. So R, carbonyl, oxygen, carbon. All right. So actually this. So we start at 1740, and then we have to do subtract or add. We have to add 30, right? So the actual signal for this molecule should be around 1770. All right. All right. Let's see some examples of that. I have some examples here. And so this table here will be really handy for you guys when it comes to this. All right, so let's go back over here and finish this worksheet here. So here you have an ester. This is an ester group. And so the ester starts on, let me see something here real quick. The esters, according to this table, is 1740, right? All right, I'm going to show you how signs work here. Is it conjugated? Yes or no? Yes. So we need to subtract 20 to 40 reciprocal centimeters. All right. So the prediction is that this will be either in between 1720 to 1700 reciprocal centimeters. The actual position for this molecule is 1715. Pretty good, right? So it's within that range. All right. Let's go to the next problem. Okay, so here we have, what kind of functional group is this? This is one of the easiest ones to spot. Ketone, very good. So it's a ketone. And so what will be the baseline number for that? So the baseline number is the first one on the top, 1715. So this is how you start off. Now you're going to predict. So this carbonyl group is in a 5-member ring. So the prediction is that you have to add 30. All right. So the actual, so the prediction, I should put here, prediction, it's 1745 reciprocal centimeters. So the actual position that you'll find in the books for this molecule is 1747. How cool is that? Now you are in full control. Once you can predict these things, it's not that difficult. All right. I have a question. If you were to pick between these two groups, and here you have your carbonyls very close, and you're unsure if it's going to be an ester or a ketone, I have a question here. How can you tell the difference between these two compounds? What would differentiate these two compounds?
You can note the benzene in the hydrogen region.
Very good. Exactly. So you have to, I put here, look at the benzene ring, or I put the benzene bands. Both of them will have sp3CH character. You have sp3CH character on both. But the benzene ring is totally different. You'll have 4 bands. Expect we have 4 bands of the C double bond C stretch. How cool is that? All right, so we're talking now, and that's next. So no, let's talk about the fingerprint region. The fingerprint region. Here you have the CO stretches. So alcohols. Let me write that down. So that this will be good for alcohols. Alcohol has a CO bond. Alcohols, carboxylic acids, and esters. They will have that. Then the other part of the fingerprint region, notice that we have a really cool band here. It's really strong, and this is the CH band. Imagine that this is what I usually think of. Imagine this is an arm, someone's arm, but this person is upside down, so this person is like that. And that person is fanning his arm, flapping it, forward and backwards, like that, flapping it like that, forward and backwards. So that is the bend. The stretch will be going like this. That's a stretch. But a bend is like getting out of the plane, is coming out of the plane. All right. So that CH goes in front and backwards and flaps like that. All right. So this is, let me erase this guy that is upside down. So this is the CH bend. All right. All right. One word of advice here for the fingerprint region: do not overinterpret. There likely be peaks here, even if there are no benzenes or CO in your unknown. That's why it's called the fingerprint region. Every molecule has its own pattern, and you will see in the lab that when we do this, and some of you already did it, the fingerprint region has a plethora of peaks there, which help you to match your unknown, which is kind of cool. That's why it's called the fingerprint region. Because of that reason, it's unique. Each compound has a unique pattern in the fingerprint region. The only thing you can assign here in the fingerprint regions will be your CO and your CH band. All right. Any questions up to this point? So what I want to do, if while you think of your question, let me tell you what my plan is here. I wanna give you experience here to see all the different kinds of possible functional groups, and something called an overtone. So I'll talk about that in a minute. And if I have time, we'll finish up. We'll introduce the UV subject, which is very short. If not, we'll just. My main goal is to finish up infrared today. All right. So here we go. One more thing here also. This advice, do not overinterpret, goes for the entire spectrum. Because I remember when I was a student working in the lab, my first time that I did research, my advisor gave me the best advice ever. He told me, whenever you read spectra, don't try to fit your molecule in the spectrum. Especially when you're doing research, we have the tendency, we want to be so positive. They say, okay, I made it. You might be making an isomer. You might be making a rearranged molecule, and you don't know. You might be in a eureka moment, and you don't know. But you're so fixated. Your mind is so fixated into getting the final product identified. You see what I'm saying? So when you do spectra, let the spectrum talk by itself. This is the best advice I can give you. So we're not going to overinterpret anything. We're just going to let the spectrum talk to us. All right? That is the key for success in this section. All right, so there you have it. All right, so look at it, what we have here. This is the first easy example. We have 1, 2, 3, 4, 5, 6, 7, 8. This is the molecule of octane. Notice that the only thing we can interpret here, it's the only functional group present in this molecule is that it has sp3ch character. All right, to start, I told you that this is your magic line. Start by tracing a line at 3000. Anything on the right side of that line is an sp3ch. And that's all we have. All of these guys are sp3chs. Check out the fingerprint region. The fingerprint region has a few peaks, but we cannot assign any of those, because if I give you a molecular formula that says H18, you know that you don't have a CO stretch, you don't have a CH bend. So none of these peaks is that on the fingerprint region, so you don't need to assign that. All right, does that make sense? Please stop me if I'm going too fast. All right. All right, so let's go to the next slide. Check this one out. Here, all right, we have, how many functional groups do you see from this molecule? Functional groups. We have two functional groups. We have carbons that are sp3s and carbons that are sp2s. All right, this is how you have to figure it out. All right, here we go. I'm going to trace my line at 3000, which I already have. That huge red line there at 3000. That's going to split my sp2chs with my sp3chs. That is the coolest thing about infrared, in my opinion, the magic line. So anything on the left of that line, this will be sp2ch signals in character. And this, all of this, notice that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 CHs that could be sp3s, but you get only 3 peaks because they are all, tangled up together. So that's why you cannot assign, you cannot say, oh, this, and this represents 3 CH peaks that are sp3. No, that's not right. This whole conglomerate, this whole thing tells you, the only thing that infrared tells you is that you have sp3ch character right here. All right, because I have a double bond, I also have, in green, I have this double bond stretching. It's like 2 rubber bands attached to the 2 carbons. They're going to be stretching out, in and out. That's the stretching that is next, and it's depicted here as the letter C. This signal, then you can represent as a C double bond C. All right, of an aliphatic or open chain molecule. This is not aromatic. All right, so here is your fingerprint region. There's nothing there's 2 peaks there, but we cannot assign those peaks, so we are not going to overinterpret it. All right, this is all we can interpret from this infrared. All right, let's go to the next slide. Let's go to this next slide. So we have a terminal alkyne, a triple bond, and then a C. All right. So if I'm giving this structure, this is what I'll expect. So I'm going to expect C, triple bond C, C triple bond C, CH, which is this one, this sharp peak here at 33. This is 3300. This signal is telling me that I have SPCH character. All right. Then I'm going to trace my magic line. And I don't see anything on the right, and on the left side, so I don't have SP2CH character, but I do have all of these represents SP3. Wait, I have a little delay here on the, hold on, what's happening? Oh, there you go. Sometimes Zoom slows down my computer. So I have SP3CH character there. All right. Also, I need to look for, if I have a triple bond, I need to look for this inflection right here. That's stretching between the two C's. So triple bond C will be this guy right here. So this is my C triple bond C. Fingerprint region, for this particular molecule, I have this pattern, but I don't have the CO band and I don't have the CH band. So I'm good. All right. Okay. Any questions up to this point? What's the first question that should come to your mind here? One that I would think of is usually my student asks me, okay, Dr. Anders, we are analyzing this spectrum and we have this structure. Seems like a straight thing, right? Yeah, it seems like a straight thing to me, but I'm teaching it, right? So I got to start from some place. The other thing is, the student might ask me, so what do I expect to do on an infrared spectrum? So for the infrared, because the infrared is not an elucidation method. An elucidation means to be able to identify something. That's to elucidate. So in organic chemistry, you will need two elucidation methods. Usually you need to have infrared combined with NMR, or you have you have MS with infrared, or you have MS with NMR. So you always need two techniques. Now, we're going to learn that NMR is the only technique that pretty much stands on its own, but you still need two types of NMR. So you'll need a proton NMR and a carbon NMR, but you always will need two things to confirm your structure. Now, by itself, infrared will not tell you the structure, what the structure is. It only tells you the functional groups. So a way for me to quiz you will be to give you the spectrum and give you 4 different structures, and then you do them by process of elimination. All right? So if I was to give you this alkyne and I give you an alcohol, an ester, and a ketone, you cancel the ester, cancel the ketones because you don't have the carbonyl groups, and you cancel the alcohol because you don't have that big, you don't have that big U-shape signal for the hydrogen, OH hydrogen, and you don't have the CO stretch in the printing region, in the fingerprint region. You see that? So now the only one that fits will be my triple bond spectrum, my triple bond molecule. See what I'm saying? So that's how you do infrared. All right? When it's only by itself. All right, so let's do this next example. This example is pretty cool. Hold on, I have a couple of questions here on the chat, maybe. Yes, pretty much, Bear. Right now we're looking at. I'm answering your question here. That we're gonna relay a lot on memorization. So. This is why organic chemistry is so difficult, because you need to have good memory and you need to have good analytical skills. So you need to be a complete student, and that's why it's so challenging. Some people are good with memory, some people are good with analytical skills. But you need to be good at both in here. But yeah, so it's mostly memorization where the bands lay. However, I will give you charts like for example, this chart, you will have the numbers, for example. Let me give you an idea. This one. I will give you the numbers. I will give you the numbers. And all you have to do is draw the functional groups. How cool is that? But you should still be able to say, okay, here's my hydrogen region. My triple bond, hydrogen region goes here. My triple bond region. My double bond region. And some books overlap the benzene ring with the fingerprint, but we're just gonna keep it like this. So this will be my fingerprint region. All right, so you need to know those 4 regions. All right, so where I was? Oh yeah, right here.
Hey, Dr. Odins.
Yes.
Do you mind going back and telling us those 4 again, please?
Yeah.
I was going to take a picture of it with my phone.
Yeah. Okay, hold on. Let me do something.
You can wait till after class if you.
No. Let's clarify that. I think just to make sure, this is the way I learn it. But I think I'm gonna fix this. I'm gonna put, just to confirm it with our current book. I think we're going to say that this is the double bond region, and here is the fingerprint region. So for the fingerprint region, all we care will be the CO stretch, which is this one. We're not gonna care too much about the nitro group, it's rare. And so we care about the CO stretch and the CH bend. All right. So here are the four regions: nitrogen, hydrogen region, triple bond region, double bond, fingerprint.
Thank you.
You're welcome. So let me save that. All right, so let's go back over here. All right. Ooh, it's saving. All right, time for a commercial. All right, everybody, stretch, just like the molecules. Oh, feels good. All right. So, any questions up to this point? Bear, you have a question? Bear is sleepy.
Sorry, I was getting a coffee refresh, but I was listening.
No problem, Bear. I'm just messing with you. Because I needed to have a commercial right now to fill in the airwaves. All right. So check this molecule out. We have aromatic peaks. We have aliphatic carbons, and we have an aldehyde. So we're gonna be busy right here. All right, check it out. So here we're gonna trace a line at the 3000, the magic line. Always split it, and what I do is I'll just continue it all the way up. All right. Anything on the left side of the 3000 are all these peaks. These are my sp2ch in character. In the lab manual it says CH aromatic. I don't like that because that also represents, you can have a double bond that is not aromatic. So it's better to say sp2ch, which I like it better. And since some of you are my students in the lab, I'm going to teach it that way for you guys. And you'll see that it's better. All right, anything on the right side of 3000, that is sp3ch. Notice that for sp2ch are all these hydrogens in green. In the green, benzene ring. B, the signal B, is your sp3CH. You have two signals, so that you have these two. You see that? Those are tetrahedral carbons. The ones in the ring are trigonal planar, so they are double bonds or aromatic. All right, so we have sp2CH, sp3CH. So the next thing we're going to identify in the hydrogen region is the aldehyde. Can you spot this, the two horns that I mentioned before? Check this out. These two peaks are about the same in intensity. And basically what you have here is you have a stretch for the CH, and also you have a bend. So you go, I don't know how to draw the bend, so I'm gonna do like rocket, back and forth, right? In front of you and backwards. So at some points it will be like this, and at some points, oh, this is better. You understand this, right? It's not a chiral carbon. I'm just telling you the movement. See what I'm saying? So those two different inflections or stretchings will make these two signals for the aldehyde, and it's the same CH. But this is what I call the two horns. So here you'll have your aldehyde group. Makes sense, right? Next in line is the carbonyl. So I have a carbonyl, and that carbonyl is for an aldehyde group. What is the signal for the aldehyde group? Right here, this one. This is a carbonyl group. And for aldehydes will be 1730. Is this aldehyde conjugated? Yes or no? Is the carbonyl group conjugated with the ring?
It is not.
Very good. Not, because we have a sigma bond, so it's not. It breaks conjugation. So it needs to be double, single, like that. In this case, we have double, single, and then double. So there's no conjugation. All right. So the signal will stay most likely at around 1730 for this aldehyde. All right, very good. Check the next set of bands. We have 1, 2, 3, 4 bands in green here. These 4 bands belong to what? Your C double bond C stretch. I'm just gonna draw one of them. I like to draw only one of them, so you can, just to illustrate. And so if I have a benzene ring, I expect to have what? They go together. A CH bend. And that bend is going to be like this movement, that rocking movement going forward and backwards. Like flapping. Like a bird flapping its wings. All right. Does that make sense? So in the book here, or this publisher at least, put 2 of them. So I usually grab or assign the tallest one, the longest one, so that the more intense one. All right. And the reason why you have 2 signals is because, okay, so these H's are different than these 2 H's, or that one in the back, or this one right here. So that's why you have multiple stretches, but we can only assign one of them. And I'll just pick the longest one. All right. Let's go to the next slide. this is an alcohol. So the moment that you see this nice, soft, round U shape, it's an alcohol. Compare that to the next slide. This is a carboxylic acid. It is sort of like a V shape that I mentioned earlier. You see that? That's the difference. Here's where it starts being nice and soft and round. And it might go like this, right? For the OH, for this OH. But because you have multiple hydrogen bonding here, you know, then that creates this mess right here. And it starts like breaking it up like that. So here's your V shape. And here's your U shape. The U shape is for the alcohols. The V shape is for the carboxylic acids. So I'm gonna delete this, but this is being recorded for you. So, all right, since I have a nice soft round curves here, that means I'm dealing with an alcohol group. So this first signal will be from an OH group. And I have it right there. And I am in the hydrogen region still. I'm going to keep on cutting or tracing my magic line. So magic lines, I don't have anything on the left side. There's no peaks here. So therefore, I don't have sp2 character, but all these guys will be sp3CHs. I don't know what's happening with the electronics today.
Hey, Dr. Odens.
Yes, sir. Landon, what's up?
Is there a correlation between the number of peaks and then the number of CH bonds?
Sometimes, but most likely not. Check this out, for example, in here. For this case, you might see something like you can say, okay, these CHs, these CH2s are equivalent to that CH2, right? So, and they are closer to the electron withdrawing oxygen. So, I would say if I had to assign that peak, it will be those two signals. It will be that peak. Now you have. Let me switch carbons here. So you have 1, 2, 3 more sets of CH2s. Those will be these ones. That's it, and they are all grouped up together. In the end, you only have two peaks, which in reality you should have 3 signals, because this CH2 here is different. This CH2 is different. You see what I'm saying?
Yeah, that makes sense.
Yeah. In NMR, you will see that, yes, we can split this molecule in half, and we will have 3 different signals, and then we can figure out the intensities based on the integrations. Yeah, but
okay, thank you.
You're welcome. But for infra, there's very little that we can assign. So right now, honestly, I can only assign, I can assign that and those. And then this guys here came grouped up here on that big blob. All right, which makes sense because it should be further from the OH group. All right, so let's do the next thing we're gonna confirm here is our CO stretch. This stretch is this one right here. Oh, no. That's the, sorry, my bad. You didn't see that. This one. All right. Here's my C. My O there. That's my CO stretch right here. CO stretch. All right. And we'll be able to now identify 3 sets of signals. Let me do this in red to keep it consistent. All right. So, we got 20 minutes. Less than 20 minutes. All right. So I'm gonna try those. All right. I'm gonna hit the pedal to the metal here a little bit. So here we have a carboxylic acid. You can recognize it by the V shape of it. Again, feel free and still go ahead and cut the magic line. So right here, this portion right here, I will call it, this is my well, this is kind of hard. Here, basically, you're gonna have to say this is your carboxylic acid functionality. All right, because you're looking at this functional group here, but for a carboxylic acid, you also have to include the carbonyl. But this V shape here only corresponds to the hydrogen bonding happening with the OHs and the carbonyl of, of two molecules, like I show you here. So anyways, to represent a carboxylic acid functional group, you have to write the entire carboxylic acid functional group here for the V shape. Next, all of these here are sp3CHs, and you have a carbonyl. What is the peak for carboxylic acid? I remember 1710. Yes, so 1710 is the lowest. That's why I remember it. Is it conjugated? No. So we don't need to subtract 10, 20, or 40. And so this will be your signal for your carbonyl peak. And that's it. The fingerprint regions. Oh, wait. The fingerprint region. We should have a CO band. This publisher. This publisher didn't do it, but I'm gonna do it for you guys. It's this one right here. That makes sense because we have a CO stretch. We need to find it. All right. Next. So basically what I'm trying to give you is experience on the different functional groups. That's my goal here. All right. What is this? An amine. See, primary, secondary, tertiary. Primary, very good. So it's a primary amine because it's hydrogens. And here are your two hydrogen stretches. All right. Don't let this one fool you. This is just a little bit. All right, 3000. I'm gonna trace my magic line. And this is sp3ch, and the fingerprint region looks really nice, but I cannot assign anything else, and that's it for this. All right, so in other words, this is 1, 2, 3, 4. This is 1 butanamine. This peaks will be especially for it. No other spectrum will have this pattern. And so that's what the fingerprint region is about.
Can you,
yes?
Dr. Odin,
Yes.
want us to put the primary or secondary or tertiary on an exam? Like, if you give us an example of this.
Yeah. So what I would do is I would just draw this. I would just say, okay, this is my NH2. You see what I'm saying?
Okay.
You don't need to put this. This is for extra teaching.
Okay.
All right? Yeah. Just give me the functional group. And I know what you're doing.
Cool.
Awesome. Let's see the next example. This is a secondary amine. So we only have one blip right there. So here is your NH group. And but feel free, you can do this. And that's fine. So here's your secondary amine. This is secondary. I'm going to trace my 3000 just to be consistent. sp character, because that's all I have. sp3ch. See, these are tetrahedral carbons and hydrogens. Boy, that fingerprint region looks awesome, but it's useless. All right, for me at this point. That's all I can assign. We're gonna set off to the next example. All right, we have a nitrile group here. Do I have an according to this structure, do I have sp or sp2 character? Absolutely not. So I'm gonna trace 3000 magic line. Every time I say the magic line, I remember Forrest Gump telling Lieutenant Dan, magic legs. So this is magic line. So here is the 3 CHs. Oh, that P looks awful. sp3ch in character, and I have a C triple N stretch, and that is this one. So if you had a spectrum like this and you don't have the structure, you might have a little bit of problem. Say for example you have, so what is this structure? Formula will be C 1 2 3 4, and then have 1 2 3 and then N. So one thing you cannot, you have to find your DUs, your degrees of saturation, and you're gonna find out that you have 3 degrees of saturation. And then when you have those 3 degrees of saturation and you don't have anything here, the only other functional group that could maybe confuse you a little bit might be the tertiary amines, but you can rule them out. Although the tertiary amine will not give you anything here because it's flat; they're flat. But this peak right here will tell you, okay, here you have it. You have a nitrile group, so you can disregard the possibility of a tertiary amine. See what I'm saying? Because you see that on the formula. All right. Does that make sense? Oh boy, we got 11 minutes. Let's see how much I can cover. All right. Check this one out. This is a good one. So here we have a competition at the 3000s. So I'm gonna draw my magic line, and it's usually pretty awesome how you can see that right anything on the left side in blue, that will be sp2ch in character. Anything on the right side will be sp3chs. All right, and here I have a benzene ring because I have sp2chs, and in this case I don't have anything here that would represent just aliphatic double bonds. Then these 4 peaks, 4 bands, these are my 4 bands, that tells me is a C double stretching. And here, what is this one? My CH bend.
The CH, sorry.
Bend, yeah. You got it, man. Is the coffee working out for you now, Bear?
Glory, glory, hallelujah.
All right.
I have a question.
Yes, Newell. Bailey.
Yeah, sorry. I don't know why my Zoom does that with my.
I know, right? It's like sounds like a first name.
Yeah, I know. So the benzene ring, for any benzene ring, there's going to be the bend present and the stretching, right?
Always. Those two will confirm each other.
Okay.
That's like a double check.
All right, thank you.
You're very welcome. All right, let's take a look at ether. This is an ether. This ether has two interesting signals here. These are your SP3s, are all this in blue, and then you have this CO stretch. Notice that it's broad because you have a pull from one side and the pull from another side, and it almost broke up here and it almost broke up here, but it didn't separate. So instead it just made a huge broad signal stretch. Try CO stretch or just write CO. Let's go and take a look at the next one. Oh, this is a tertiary amine. Notice that all over here is flat. All right, the magic line is going to play a good role here. And here I can split these two signals. So on the left side of 3000 I have sp2ch character. On the right side I have sp3ch character. I have a benzene ring. Here's my 1, 2, 3, 4 spot, 4 bands. Sometimes you might have 2 bands. Sometimes you see that they start like combining here or here. Yes, so in this case I only see like 3 of them, but it's anywhere between 2 to 4 bands. And so here are your C double bond C bands. And right here you will have your CH band. All right, very, very good. We keep on cruising here. 6 minutes. I gotta give you more examples. Yeah, I'll have time. All right. Oh, the next thing I'm gonna talk to you about is an overtone. Check this thing out. What is an overtone? Okay, an overtone, it's when people accidentally makes the sample concentration too high, and so the carbonyl will reflect at the beginning too. So basically it's like saying that this carbonyl went like this. So this little piece is gonna show up over here. Kind of like that. So anyway, so an overtone, you will identify it, and don't let an overtone trick you thinking that this is not an NH. All right, it's not. So this is one of the times where I want my students to wise up. Hold on, I'm gonna cancel that. It's not that. How do you identify the overtone? Notice that usually for the overtones you go to the carbonyl, and most likely for the carbonyls I will give you the number if that's the case. In this case is, hold on a second, let me change pens. In this case is 1685. So an overtone is equal to 2 times the carbonyl. So we have 1685. Let me check that with my calculator real quick. So I have 3370 residual centimeters. All right. Okay. So I'm gonna assign this as the carbonyl because notice that this number is kind of low too for a ketone. So a conjugate ketone starts at 1715 and you subtract 20 or 20 to 40, right? So your range will be 1695 until 1675 per centimeters. And that number is right in the middle. This number is right in the middle. So we're good. So this, we're dealing with a conjugated ketone. All right? With an overtone. So this overtone, kill it. All right? So trace the magic line at 3000. Anything on the left side of that line is SPHs. Anything on the right side is sp3CHs. Here's my sp3CHs. Here are my sp2CHs. All right. All I need to do now is assign these peaks here. These peaks are my C, double bond C, stretches. Oh boy, I cannot move this thing. Crowds. I move it.
Hey, doctor.
Yes. And
the C double bond C stretch. Those peaks, so they can have like that pause in between the 4 peaks, right? Because that's what I'm seeing on this.
Oh yeah. So here you'll see them 4. You have 1, 2, 3, and 4.
Okay, so we just got to make sure that they're in the area.
Yeah, in the area that at the beginning, what we mentioned it here earlier.
Okay.
Where is it? Right here. So they should be around here. 1600 to 1450.
Okay.
All right.
Thank you.
You're welcome. And here's the CH band. My computer is. This is the band. I need to fix this because you notice that I moved this thing to the left side, to the right. I have to kind of like do this. Oh, it's a pain. All the other stuff stay behind. Oh, I can move it. So that will be a lifesaver. Oh, nice. Need to move this a little bit to the left, kind of like that. All right, fixed. We got 1 more minute and 2 more infrareds. Let me go over this real quick. What do we see here? This one is telling me that I have an overtone again. This is an overtone. Ignore that, because this will be 2 times 2. So it's 4, 8, 14, 33,485. That's right around here. So if I had that number, I know this is not an NH. You see what I'm saying? So make sure you do that. You have the magic line here. This will be sp3CH. You have a carbonyl group, and that represents an ester. The ester will have a CO stretch, and that's all we can assign to this. Give me 30 seconds and I'll go over this one so that you have them with you. Here again, this is a an acid, an acyl chloride. Oh boy, Zoom is really slowing down my computer. So anyway, you have it here. Here you have sp2ch on this side, which are all these signals. You have an sp3ch character. You have a carbonyl group. You have a little overtone. You see that? So this number times 2. This is your carbonyl. Oh, already drew it. You have a benzene ring. So what I'm trying to do here is one of those brackets like that. Sorry. And here's your CH bent, and we finish. Thank you, guys. I'll see you next week. Have a wonderful day.